At this point, we know the big picture. So we would like to go back to the electronic problem and then see how we can possibly do anything to solve this n electron problem. By itself, it is also a problem that cannot be solved. It is an n electron problem. Even for H2 molecule, there are 2 electrons. So it's like the helium atom problem even for H2. So it's quite difficult to do. Here, I would like to introduce again the main idea of a way to move forward on this electronic problem. So let's look at the electronic problem for the simplest neutral molecule, H2. Here I write down the H2 hematonia. The physical situation is I have A, B nuclei, they are proton now, and then I have 2 electrons at R1, R2, okay? So the 2 nuclei, I could use the reduced mass and then, let me see, I cannot do it here, right? I cannot do it here. Okay, so this is the kinetic energy of electron 1, kinetic energy of the electron 2, and then electron 1 sees nuclear A, electron 2 sees nuclear, electron 1 sees nuclear B, electron 2 sees nuclear A, electron 2 sees nuclear B, then the 2 electrons repel and the nuclei are separate at a fixed R. That is a parameter, there's a constant term, all right? So this is the electronic Hamiltonian multiply the electronic wave function equals the eigenvalue we want to solve times the wave function. So this is the electronic part of H2 molecule. It is a 2 electron problem, 1 for each value of the separation. So many problems to solve. Don't worry, no one can do it, so we don't need to do it. There's no analytic solution for that. Nonetheless, there are many numerical solutions. So there are good answers for you to compare with when you make some approximation. So the idea is the following. We try to approximate it into single electron problem. The electron part, just average, some average potential energy of one or the other, things like that, okay? That we will not do it in detail because the key point here is about how bonding comes up, okay? We have discussed this Hartree-Fock thing in the atom concepts. They applied also in molecules and in solids. So the idea, again, is to reduce the problem to single electron problem. And then after we have this single electron state, we fill the electrons in according to the Pauli exclusion rule. Just to remind you, behind the Pauli exclusion rule is the requirement that it is anti-symmetric wave function. So, just as advertised, H2 is very difficult problem. No one can solve it. To illustrate the idea of how bonding can be achieved, let's look at the simplest of the simplest molecular problem. But it is not neutral. It is the problem of H2 plus iron. First thing, it exists. Okay, now, so we are not talking about something fictitious. This is real. You can take a hydrogen molecule, ionize it, meaning take out 1 electron, take it to infinity. The remaining thing here is called H2 plus iron. Okay, the full name is that it's a molecular ion because there are two nuclei. What is it? There are two nuclei plus one electron. That is the trick. We want to understand bonding. Okay, now the question becomes very interesting. If you are this electron, what would you do? There are two centers. Would you go to this side alone and form a neutral hydrogen and then an isolated lonely proton? Or you bias this side in the same way? Or you are so clever that you could, there's a wave function, okay? You're going to spread yourself skillfully so that one electron, you can bind two things. You can bind two centers. If that is possible, how? Okay, so do you understand the question? Okay, the main thing is that this thing exists. It is there. Okay, it is a physical fact that we want to explain. The answer at the end is that even understanding this bonding, you will see bonding is entirely quantum mechanical. There's no classical analogy in the term at the end. Okay, now nothing new. You have seen such a thing, right? The exchange integral, things like that. We will see something rather similar. Okay, so let's proceed. That exists. One electron can bind two centers. How? What is the wave function? How will the electron, the probability density, spread in this region? So let's work this easier problem out. Here, I try to draw a picture of it so that you understand what I wrote down. AB, separation given as R, this is a parameter. One electron only, the coordinate from something called the origin, so center of mass, for example, is small r. The separation from the electron to A is called RA, the other RB, etc. Okay, so as simple as that. One electron only, so no electron repulsion. Things should be easier. So let's write down the Hamiltonian for H2 plus. Single electron kinetic energy. Electron sees A, electron sees B. There is a constant. The two nuclei repel. Okay? This is just a number. Just write it there, set it on the side. Then let's look at what is the structure of the Hamiltonian. Just like any single electron problem, we have a kinetic energy term, we have a potential energy term that the electron feels. It is just a function of R because we only have one electron, okay? So I can collectively write it as a potential energy felt by the electron, one only here, V of R. Behind the scene, the picture is the electron sees two nuclei, okay? Then the problem becomes, we want to solve this Hamiltonian for the H2 plus H psi equals E psi. So this is the problem. Just to remind you, we have many problems to solve, namely, give me a separation, it is one separate problem. So we have to repeat this problem many times. Therefore, we can label it as, you give me an R, there is an eigenstate, and then there is some eigenvalues. Then I need to repeat for a different R, then I have a different eigenvalue. So at the end, I have the curve, okay? So equation 16 with this Hamiltonian will be our problem. That doesn't look very difficult, right? Single electron, but there are two centers. So it will be good to look at how this thing look like. This is V of R. So here, I try to draw some picture for you. Now it is a 4-dimensional picture because V of R is already 3-dimensional, okay? So here, I just think about the following thing. I have a nucleus here, I have a nucleus there, okay? Now, this is a proton. A proton will provide a -1/r Coulombic potential. So it's something like this. A proton here, -1/r is something like this. 1/r is like that, 1/r is like that, okay? 1/r is like that towards you, towards me. So the whole thing is something like that, but it is only a 2D version, okay? So follow me. I have A, there is a -1/r. I have a B, there's another -1/r. Do you see that? Here and then there. But I need to add them together. Therefore, in the middle between A and B, it is minus something, add to -1/r, it becomes more minus. So it is like this side, I have that, but in the middle, I have something that is deeper, more negative, and then this side, -1/r. Follow me? In the following page, I'm going to draw it A and B. I go along this line through A and B. Actually, I can go through the whole plan, right? There are many different pictures, but I draw this line, okay? And then see how the potential behave or vary as a function of this position. So this is the figure. I hope that you get the point now. I draw it for different separations. When the separation is very big, that is to say, the two hydrogens are far apart, then the -1/r here already becomes, so this is like -1/r behavior, Coulombic, okay? So this is also another -1, but this, you understand that this is away from A, this is away from B, all right? So the two sides, but only when they already approaches 0, they meet each other. So you don't see much very different behavior there. However, if the separation are closer, so this is a different R, closer, as I said, -1/r add to another -1/r, this will be more negative in the middle, okay? Even closer, then you see the V of R becomes different, okay? So do you get this one? So this is the V of R that goes into the Schrödinger equation, okay? So let's get back to the Schrödinger problem. The problem is, I copied the Schrödinger equation here again. Just to remind you, this is just a number. Thereby, I can subtract this number out to the other side and worry about that later, okay? So therefore, I can take this, it is a constant. So the operator is a constant operator. So everything goes into it will just give you the number times itself. So it is not going to hurt us. We can handle it later. What I mean is that for the moment, for example, you don't worry about this constant and solve this problem. Okay? If you know that, that is the problem that I wrote down. If I solve this problem, I call this eigenvalue discrete energy, funny E, okay? And after I solve this, at the end, I add back this constant that will be my energy for this original problem. Okay? That's all this page is saying. There's a constant, don't worry about it. We do the important part first, at the end, add this thing back, that's it. Okay? Therefore, at this point, our focus shifts into solving the first equation without the last term. So this is this equation. So we solve this part first. The answer, remember to add back this repulsive nucleus potential energy, Coulomb repulsion. Okay? That's rather obvious. And now is the punchline for this part. Instead of solving this analytically and exactly, we will make use of what I would say is one of the most beautiful approximations in physics. It is called LCAO and then hyphen MO. This is what the chemists call this approximation. The full name is linear combination of atomic orbitals will be a good approximation to the solution of this molecular ion Schrödinger equation. The resulting thing, after you linear combine this, the resulting wave functions will be called molecular orbitals. This is in analogy to atomic orbitals for helium, for all the other thing. And after solving that, you can fill the electrons in, okay? But for the moment, we are not worrying about filling electrons in. We are worrying about solving the Schrödinger equation. What are the wave functions for the molecular states? That's the question, okay? Now, at this point, just to remind you about the technical skills we introduced in week number 1 of our course, variational method. When you see a trial wave function of linear combination of functions of bases, how many you use, then that will be a matrix problem of that size. You use 6 functions, you will get 6 by 6. You use 2 functions, you will get 2 by 2. We even know the matrix elements form. Okay, so this will be the idea behind the approach. So let's move on. What does this mean? Okay, pay attention. Something very simple, but very natural and profound will follow. If you can't follow what is going on in this H2 ion problem, here are some easier analogies to help you follow what's going on. We can always, it is a very good picture to think in terms of wells, finite wells as atoms, but just 1D version of atoms, of course. So, because we know that in a finite well, we have this states. So, even more, the ground state is something like that. That looks like an S state. The first excited state is something like that. That looks like a P state. Well, in terms of some symmetry, one side is plus, one side is minus. So it's like a P state, the 8, okay? One is plus, one is minus. So it's a very good picture to think about atoms as a finite well. And now what is a molecule? A molecule will be, you bring 2 wells together and the barrier in between is rather thin. That is to say, you let the two wells couple. That will be an AA molecule, right? Even more similar to our problem, we saw that the V in the middle is shallower because minus plus minus. So it's even more like this. So think about this. But if you have two different atoms, that's fine. How about one shallower well and one deeper well? So this is an A atom, this is a B atom, that will be an AB molecule. Okay? Now think about it. If you are given such a problem, I think you have in your mind one way to do it, right? You will write down the wave function in region 1, 2, 3, 3 is in the barrier, okay? 4 and 5, right? Decaying, oscillating, things like that. And then you use boundary condition to connect them up. Then you have a set of equations from which you can solve for the allowed energies. Okay, do you follow what I'm saying? Do you want to do this problem as a homework problem? I think it's meaningful. So, I mean, okay, so this is one way to do it. Okay, now if you follow what I'm saying, and you know this is one way to do it, that method simply means you take this problem as an entirely new QM problem. By that I mean, you make no reference to this single well problem. You take it as an entire new 5 regions, 1, 2, 3, 4, 5. Okay, you write it down, join them, boundary conditions. Of course, that works, certainly. All right. But my remark is that doing that way, you are taking it as a separate and independent, a new quantum mechanical problem. How about this? We make reference to this single well problem. We know the solution here. Can we think about the answer to this problem as being formed by linear combining these solutions? Okay, so that's the idea. So I have something on the next page. How about this? I make reference to the single well situation. That's my atom. So left atom, I have ground state, first excited state. Right atom, I have ground state, first excited state. And now they come together to form a AB molecule. It's an AA molecule. It's an A2 molecule. Okay. Instead of solving this problem entirely from scratch, I would like to make reference to this atomic states. Immediately come to our mind is when we want to solve for this, maybe I take the ground and first excited state on the left, and then I take the ground and first excited state on the right. R means right. I form a linear combinations of the ground state from left and right, and first excited state from left and right. I take this as a trial wave function. At least everything is legal, huh? Okay? Then I can plug this into this new H, right? And then set up a 4 by 4 matrix I hope that you follow me after the midterm, okay? Okay, a 4x4 matrix. Then we can solve for 4 eigenvalues. If we want the lowest one, then we take the lowest one and say, that will be a good molecular ground state. Okay, do you understand what I'm saying? This is the essence of LCAO. Making reference to the atomic states of the atoms forming the molecule. Okay? Okay, any question up to this point? This line basically motivated LCAO. Any question? Okay, now if not, good, that is LCAO. All right, now I have many comments to make, but that is the idea. You have atoms to form molecules. You know the atoms. We have 1s, 2s, 2p, things like that. Why not making use of the atomic orbitals? Use them as bases and then mix them together to form molecular energy eigenstates. Okay, now the first advantage I see that is that it is physically transparent, meaning you can trace this molecular state comes from A atoms 2p and B atoms 1s. Now that will be the case for HF. The hydrogen, of course, it has a 1s electron waiting to form some bond. The fluorine, it is one less electron from full shell. So it has a p state that has only one electron. So if I linear combine the 1s of H and the 2p of F, I can form this bond. So it is what I meant by physically transparent. Second point, here I draw two atomic orbitals here, then I linear combine them. The question becomes how many to use, okay? For an atom, I could start with 1s, 2s, 2p, all the way up. Actually, never ends. How many should I use, okay? Well, the lazy answer is the more the better, okay? Include more because the basis will be more complete, you know, in a lazy mathematical way. But that is too lazy, right? Practically, actually, a better answer is to be guided by physics. Just as the example I showed, I just mentioned HF, you have to look for where are the outermost electrons that will be responsible for chemistry. Bonding has to do with atoms forming molecules. It is kind of chemistry. It must have to do with the outermost electrons. So for the fluorine, 1s is completely filled, 2s is completely filled, 2p, there are 5 electrons, so only 1p orbitals is not completely filled, okay? So for the hydrogen, it's 1s, so you better use this 2px, for example, and this hydrogen 1s. You use this too, you already capture the key bonding. Of course, if you like, you have computer power, you can include 2s, 2p, or all the other things, fine. But that will not improve very much, okay? The key physics is already captured if you are guided by good physics. So let's continue with this model molecule. Let's get back to our problem. So we have this AA molecule in 1D example. Think for yourself. What will be the ground state? Okay, so you know something, I hope. This is symmetric ground state. Don't cross zero, no notes. But that is a barrier here, the wave function to go to zero. So 0, 0, okay? Well, the potential well is deeper here, so better make use of this to lower the energy. So I may have 2 bumps. But I don't want it to cross zero, and yet it is symmetrical potential well. So there must be a left and right symmetry because the atoms are the same. So what else can it be? It must be something like that. Okay, do you understand what I'm saying? This will be a good guess. Okay, now, for those who want to do the 5-region thing, fine. You will write down an exponential thing, an oscillator thing, an oscillating thing, or decaying thing, doesn't matter. Oscillating thing, a decaying thing. So you measure it, you will get this. Okay? So roughly, you see that. Now, LCAO. If I only use this ground state, left and right ground state, and combine them. That is to say, I only use 2 terms. I don't care about the first excited state. Left, right, add them. It's not bad. Do you see? Okay, do you get the point? Okay. Now, even more. How about the first excited state? Now you start thinking about the same thing. Okay, symmetric, but I want 1 node. Better cross as 0, symmetric, right? And well, at least the wave function square should be symmetric in the middle, but now with 1 node, so it's something like that. Decaying away from the barrier. Okay, now if you use the ground state, minus the other one, so it's again a linear combination, but not plus, but minus, this one will become negative. Okay, so this one will go into negative, will be something like that. Okay, so this add into that will give you this. Do you see? Okay, so that is to say, for this problem, I can even see it that if I use the ground state of left and right, as simple as that, I will get some rather good representation or approximation for the ground and first excited state. Okay? Now, if you are not satisfied with this accuracy, fine. You go back and include the excited state in the atoms, set up the 4x4, you get 4 eigenvalues, you take the lowest 2, that may be more accurate than just taking the first 2 combinations. Okay? But those are about accuracy issue. It's not the conceptual issue. So let's go back to our H2 plus problem. We play the same game. We have a left hydrogen, we have a right hydrogen. Hydrogen, we know we have a lot of atomic orbitals. We have a lot of atomic orbitals. So formally, how about this? Hydrogen, give me all your state on the left, on the right. Okay, they center at different places. Okay, now by that I mean the left one, the ground state will be R minus where the first nucleus sit divided by the Bohr radius. That will be the ground state. Okay, because it's center and the A nucleus. Otherwise, we know that this is a decay with Bohr radius. Now, formally, we should form a LCAO using all the atomic state on the left. So the I will label 1s, 2s, 2px, 2py, 2pz, etc. And then also using all from the right atom. If you do that, it's still exact. They form a complete set to solve, to expand this molecular state. But of course, it is too complicated. The matrix will be too big. Again, we should be guided by physics. For the H2 plus, we know even H2, we have one electron on 1s, one electron in 1s. The 1s must be most important for doing chemistry. You worry about the 4f, what for? They are empty. Empty there, you combine, or there is a state, but it will remain empty. You only have 2 electrons, right? H2. Okay, so be clever, think like a physicist. Therefore, the simplest situation for H2 plus is to simply say, left atom, give me your 1s. Right atom, give me your 1s. Okay? Then I form a linear combination of the 1s. That is the simplest possible linear combination of atomic orbital. So this is LCAO, the simplest version, simplest possibility for this problem. Okay? That is to say, I use a basis of 2 atomic orbitals. 1s left, 1s right. That's it. So I have 2 coefficients. They are unknown. You can do variational calculation to find them. Okay? But for this problem, it is even easier than that, for the reason the 2 atoms are the same. Or else, the potential has some symmetry. For the reason of this symmetry, we know one thing. If this will be the square, will be how the electrons density will be distributed in space. Okay? So now, think about it this way. I have a left and a right atom. Wave function square will be how the electrons spread itself, right? Okay. Now, first of all, they are the same. Proton. The electrons should not bias any side, right? They are the same. How could the electron distinguish a left from right? No way, okay? Or else, if it did bias one side, on my side, I will say it is biasing the left atom because I'm standing here, okay? Then on your side, you will say, no, it's biasing the right one. But they are the same, okay? So it doesn't make sense when you have identical nuclei. So for that, we know more than just this LCAO, this form, C1, C2. We have more to expect due to symmetry. The electron will not bias any one side. That is to say, the wave function square will be symmetric in the middle. All right? So with that, we already know the possible linear combinations without doing the variational calculation. Of course, if you want to do it, doesn't matter. Why can't both bias state be ground state? Oh, have you seen anything that is degenerate ground state? At least up to this point, no, right? Can you give me a problem that you have degenerate ground state? No. Oh, have you seen any 3D problem with degenerate ground state? Ah, okay, think about it when you have an example come to me. All right? Okay. Now think about 3D harmonic oscillator. The ground state is unique, right? The 3 quantum numbers are 0, 0, 0. So that is your midterm problem, something like that. Okay. So now let me go on. So even without doing the mathematics, we already know some answer. So let's try this left 1s plus right 1s situation. Here I try to draw you the picture, all right? Now, what I'm linear combining is the following two wave functions. 1s has the form of exponentially decaying with the bore radius as the length scale. But we have two atoms, two centers. So one is centering at A, so it is decaying from this nucleus. The other is decaying from the second nucleus. And the length scale is half an angstrom, about, okay? So there is an R. Then you can think about it. If it is very far away, the plus one doesn't feel each other much, right? Decay to very zero, and then add to this one, okay? And the plus and minus one will not make much difference, actually, okay? When they are very far away. However, when they are closer together, the plus one will be very different from the minus one, because the plus one will give you something like this. Because it is decaying, but it meets the other side, they add up to something bigger in the middle. You started to see covalent character, okay? However, the minus side, the one will be like that. In the middle, it is zero because they minus, okay? So very different when the spacing is closer, okay? So now let me move on with all this big picture already conveyed, okay? And here is one remark that I make very early on when we do the variational calculation discussion. Look at this basis. They center at two centers. It is an example where formally S12, they are atomic orbitals center at A and center at B, just like this picture here, okay? Now, there is no quantum mechanical regulations telling us that S12 should be zero. In fact, it is not formally, okay? Get it? Don't think about that they are orthogonal or anything. They belong to two different atoms. That is the formal statement. However, you also see that the overlap range is tiny. Therefore, even they formally are not zero, they are not going to be big. Okay? So very often, when you are in a hurry, you don't want to calculate this thing, approximate it to zero, it is okay. But you must realize that it is an approximation rather than it is a formal requirement. It's not. 1s left, 1s right, depending on the extent they overlap. That will determine this integral, okay? This integral goes into the matrix element here, okay? This is just a remark. So now I want to get the punchline through before we end today's classes. Without doing any calculation, we know one thing. The two coefficients should be the same or they're only off by a sign, okay? So here is my argument that I just made. Due to symmetry, it can't bias any side. We know that this square should be equal to that square, the coefficient square, because they are basically identical nuclei. Okay. Now, there are two choices. So the coefficients are the same or they are off by a sign. They will give this one okay. Therefore, I will have two cases. If they are the same, they can factorize out. I can determine it later in a page. Then I have this 1s left add to 1s right, or 1s left minus 1s right, okay? This is exactly like our two well cases. So let's look at two different cases. Very far away separations, okay? So I have left add to right. The square will be something like that. Or left minus right, but they're very far apart. In the middle is already the very exponential tail part. So you add them, you subtract them. So this is flipped to negative. The wave function is like that. You square it, more or less no difference. This is the case for large separation. Okay? I will tell you what it means in a while. Okay? But the most important situation is we have to try different separations. Okay? When we try different separations, you will see the difference. Left plus right, you will have an enhanced wave function in the middle part between the two nuclei. Taking the square, you will have more probability. You will have some probability, at least it's not zero, okay? Some probability of finding the electron somewhere in between the two nuclei in this region. This is what you learned about covalent bond in high school. The electron can be found somewhere in the middle of the two nuclei. But quantum mechanically, there are more probability closer to the nuclei, okay? The point is that there is appreciable probability in the middle. However, if we take the minus combination, okay, that will be very different. It is decaying, and then in the middle, this side is also decaying, although not to zero yet, but when you minus, this minus add to that must be zero, okay? That's why you have this node. Or in 3 dimensions, it will be called a nodal plane. A plane where there's a zero in the wave function, okay? And by R, you see that this is of higher energy, should be, right? More curly, things like that. And then if you square it, this is the probability densities of the electron. You see that you will have no probability in the midpoint, midway between the two protons, the two nuclei, okay? So summarizing, these two LCAO will form two possible molecular states. Don't worry about this. Well, try it. Don't worry. Well, that is it's too mathematical for me. Sorry. Okay, I am a very practical person. Okay, don't worry about it. Now, okay, C1, C2 can be complex. You go into the variational calculation. You have 4 things to vary. You vary 2 of them, you will get 2 equations. Okay, you vary the other 2, you will get 2 other equations that are the complex conjugate of the 2 equations you are playing with. You get the matrix done. You will get the eigenvalue. You use the eigenvalue, go back to solve for C1, C2. Then that answers your question. Put. Get it? Okay. That's a long procedure. Okay. Then if you do that, but again, go back to my first answer, too mathematical for me. But I outline the approach to you. Okay. So let's get back to something very physical, not mathematics. Quantum mechanics is very physical. Let's do it. So summarizing, as a function of the separation, the bonding one, you will have enhanced increasingly wider separation, narrower separation. You have some probability in the middle of finding the electron. This -1, 0, you have a nodal plan in the middle. As I told you, there are numerical solutions, very accurate one. So here I meant to compare the exact so-called numerical solutions and then with our LCAO, okay? So here are the more accurate solution, but you see the same behavior. Okay, so it's quite okay, LCAO. And now, now I will just sketch you the answer, and then I will come back to this point after your so-called reading week. Okay, I hope that you do read. Now, if we want to do something more seriously, we should do the following. We have this LCAO as trial wave function. We set up the 2 by 2. Then we solve the 2 eigenvalues, okay? Or else, the same, equivalently, we can use the 2 linear combinations, the +1, and find the expectation value of the Hamiltonian of H2 plus. Either way, they mean the same thing, okay, mathematically. Now, the answer is as follows. I will do a little bit of this page and then I will end because that already is the purpose. It's a very complicated page, right? Don't worry, I guide you through. If we do this so-called bonding combination, that is to say, add them together, okay? We use this and put the H2 plus Hamiltonian in between, okay? And then calculate the expectation value as a function of different separations, we will get this curve. Okay? This one. You see this one, okay? But remember, at the very beginning, we take out a constant due to the nucleus repulsion. This is this line. Therefore, for the electronic result, we should add this line, I mean this one, into this one, okay? And the final answer is this. You see my cross, this line? This particular line, okay? Get me? Now, let's look at this particular line, especially there's a minimum. How wonderful, okay? We see that there is a minimum and the reference energy is minus 13.6 eV, okay? It is referring to two cases, linear combination actually. The electron go to this side with a lonely proton, the electron go to this side with a lonely proton, okay? If you use that combination into the Hamiltonian, you will get this eigenvalue. But you see there is a not very profound minimum, but there is a minimum. And there is a preferred separation. The preferred separation goes from here to here, okay? So it is predicting something like 1.06 angstrom as the best separation of H2 plus. And it gains a binding energy of 2.6 eV. Now that is rather big. Room temperature is 0.025 eV. So there is a binding. One electron can bind two protons. The preferred separation is about 1 angstrom. The energy gained is 2.6 eV. That's the answer from a very simple LCAO calculation, okay? If you do the -1, it will give the other curve. You do the -1, it will give you this curve, but that is not the whole story. There is a constant, you need to add up the repulsion, okay? At the end, you get this curve. For hydrogen H2 plus and hydrogen, you don't see a minimum, okay? Now, once upon a time, you must have heard about bonding and anti-bonding, this kind of adjectives. It happens that this is the place where these two terms comes in. The +1, when we see the minimum, we will call it bonding. The second one, we don't see the minimum. That's why we have this funny word called anti-bonding. It is just for this particular case. There are other cases that actually there are also minimum in the upper curve. It has to do with what is the atoms forming the molecule, okay? So now the end story is that we have 1s from atoms coming in. At the end, we will have a lower molecular state called bonding. We have a higher state called anti-bonding, okay? And we have one electron, it will sit here, it gained some 2.6 eV. Have you seen this kind of diagram in chemistry? This is the quantum mechanical story of such diagrams, okay? So I will end here today. You have a reading week coming in the next week, so I will see you quite some time later, okay? So goodbye for now. If you have question, I will answer it. I will stay and answer it.